In this next question, organic chemistry, so what we have is butanol, which is an aldehyde. So you got the CH3, CH2, CH2, and then CHO functional group there. CH3, CH2, CO, CH3. So this is a ketone. As you know, these 4-carbon aldehyde and 4-carbon ketones, they are what you call structural isomer. And in that structural isomer group, they are specifically called functional group isomer as part of AS chemistry. We've done a couple of tests here. So something that reacts with butanol and butanones. So it reacts with both carbonyl of aldehyde and also ketones. So it can't be oxidation. It has to be your 2,4-DNPH. That is the proper name with all the letters capitalized. Or if you want to name it in full, it's called 2,4-dinitrophenylhydrazine. If we know that hydrazine is NH2NH2, this is just your typical hydrazine. But then you replace one of the H with this benzene group, a phenyl, and then you add on a NO2 at position 2, and then you add on another NO2 at position 4. So 2,4-dinitrophenylhydrazine, that is your 2,4-DNPH. That will give you an orange PPT with both aldehyde and ketones there, following a condensation reaction. Condensation as stated in the AS syllabus. Now it reacts with aldehyde but does not react with butanol. So we are really looking at Fehling or Tollens, which is specific oxidation, very, very specific oxidation of your aldehyde. So in fact, you can use dichromate 6 acidified as well, but I'm just going to use the usual one, which is going to be like your Fehling solution, which is blue in color. Or you can use Tollens, which is a colorless solution containing your silver plus, which will give you a silver mirror. Or you can use the orange color dichromate 6, which will oxidize the butanol when you reflux it, but it will not oxidize the ketone, so it will remain orange. You'll see orange to green coloration there. As for the last reagent, it doesn't react with aldehyde, it reacts with ketone. So not many things will react with ketone only without aldehyde, but hopefully you can see the very specific CH3CO. This is called the methyl ketone as stated in the AS syllabus, the iodoform test. The iodoform test will chop away, it will fragment away this CH3 at the end there. It will fragment away as CHI3 triiodormethane, the iodoform test. Okay, so it has to be alkaline. It won't work without alkaline conditions, and then it's aqueous iodine, I2. Okay, or what you can do is you can write OH minus and then I2 aqueous. That would be okay as well. Now when M reacts with butanol, so M is going to be the oxidation of this aldehyde. You want the organic product, you don't want the inorganic product, you don't want the copper 1 oxide, you don't want the silver mirror, you want the organic product when you oxidize the butanol. When you oxidize the butanol, you are going to get carboxylic acid. So 4-carbon carboxylic acid there. What is observed when N reacts with butanol? N is your alkaline aqueous iodine. It will fragment away this thing as a yellow precipitate of iodoform. So you don't see iodoform. Instead, what you see is a yellow precipitate. So this yellow precipitate is your iodoform, which is your CHI3, and that forms. What type of reactions is occurring when N reacts with butanol? Well, in a way, when you react with butanol, one of your product is actually going to be a carboxylate. We don't get a carboxylic acid. We get a carboxylate and we get a CHI3. We get a carboxylate instead of carboxylic acid because of the alkaline or basic condition. So you never ever get carboxylic acid until you add excess acid to neutralize the OH minus. Only then you can get back the acid. Otherwise, you always get the salt. And this reaction is essentially the oxidation of ketones, because follow this carbon here, this carbon original of the ketones now has gained oxygen. You lost the carbon that is not oxidation, but you gain oxygen atom, that is oxidation. So what type of reaction is this? This is definitely oxidation of the ketones, or you can say redox. Why redox? Because the I2 has gone to iodine -1 in the CHI3. The carbon of ketone gains oxygen. So, gaining oxygen there, that is definitely your oxidation. And this question can actually ask you explain why. And this is inorganic stuff. So this is iodine 0 oxidation number going to -1. Decrease in oxidation number is definitely your reduction there. Okay, I just simply call it redox, but if you call it oxidation of the ketones, I'm sure it will be accepted as well. In this next question, we have organolithium. You don't really deal with organolithium as part of organometallic chemistry. I was actually an organometallic chemist, but that was a while ago when I left my PhD. So, it brings back memory actually. So what you have there is a source of CH3 minus. So you have a lone pair on the carbon there. This will act as a nucleophile. That's what they're saying. It has a lone pair that allow it to act as a nucleophile. Now this reaction between we call it actually, methyl lithium, short form milli, and carbonyl compound can be used to make alcohols. So this mechanism is going to be from your AS, called nucleophilic addition mechanism onto ketones and aldehyde. The first thing you do is label the dipoles. They already shown you the lone pair there, not from the electrons, from the lone pair. From the lone pair, rich in electrons, the first step is attack the electron deficient or poor in electrons. After that, you break the carbon-oxygen double bond. And then in doing so, you will get an oxy-anion intermediate. It's an oxy-anion because you have a negative charge on the oxygen, and this lone pair is now on the oxygen. And what happened then is it will protonate. So this is protons with no electrons. So when you add in the H+, the lone pair picks up and donate and form dative covalent bond. It will just pick up and form a normal covalent bond to produce your alcohol there. And this is your oxy-anion intermediate, very similar to your AS nucleophilic addition, except that you're not using Cn- or H-, you're using a lone pair on the CH3- there. Now this very last bit of this question, this is about working backward. If you want to prepare this alcohol, work backward. What do we have? Well, we are going to get it from this thing here. So CH3. If I just focus on this O-, and then I have a H+ like this. Well, not really H+, but I have a H. Let me see if I can use a different color. I have a black color, a H like this. So compound G from butanol. So where is your original butanol? Your butanol is going to be that is not the color I wanted. 1, 2, 3, 4. So that is your original butanol. If you think about it, 1, 2, 3, and then 4, like this. So which means, what is your reagent then? I hope you can see that your reagent is going to be this one here. So what you must have is, you must have CH3, C, and then CH3. There is already one hydrogen there, so there is one hydrogen there. There must be a lone pair on this thing here. Previously, you have CH3 like this, because this one was basically this one. But now instead of CH3, you have instead of 3 hydrogen, you have CH3, and a hydrogen. We are just working backwards from this aldehyde plus this thing here. You will get addition of these onto the carbon, and then you get O- that can protonate, pick up a proton to give you the alcohol there. So we're looking at the structure of the organometallic reagent. So I could draw it like this. If you want, you can draw it a bit better, I guess. I don't know how you can draw it better. Probably like this. CH3, and H. It really does not matter where you put the CH3 and the CH3 could be there and there because these are single bond. They can rotate, the molecule can rotate, the ion can rotate. But what is important is show the lone pair and show that it has a negative charge, just like the original question. Show the lone pair, show it has a negative charge. Just working backward for that 1 mark there. Okay, so hopefully that makes sense there. And that's it really for this 10 mark organic question.